Okay, here's problem 4, where we've got neutron stars rotating at really fast, basically. And the stars are radius of 7 kilometers, and what's its minimum mass? So this material on its surface remains in place during the rapid rotation. So the idea here is you've got this big neutron star, which is extremely dense, and it's got a radius. Let me draw it bigger. Okay, and it's got a radius of capital R, and it rotates with a certain frequency. So frequency is given in rotations per second, or revs per second. So let's see, how can we find out how massive this thing has to be to keep all its stuff in place and keep it from being flung off by the spinning? So this is just simple, circular motion. So say we have like a little chunk of neutron star mass on the outside of this thing. It's moving at speed v, right? And it needs to be accelerating towards the center of the star in order to stay in place. And that acceleration, where does that come from? Well, the gravity of the star, right? So there's got to be a gravitational force on it. So that's sort of a sketch of how we're going to do this problem. Now we need to find this velocity here, or its speed on the surface, really. We haven't dealt much with frequency, but what I can tell you is frequency is number of revolutions per second, and we have dealt with period, which is number of seconds for one revolution. So t is measured in seconds per revolution, frequency is revolutions per second, so I think you can see that t is going to be 1 over f. It said it revolves 100 times per second, so that you can see how that means that it takes 0.01 seconds to revolve, for my numbers anyway. Okay, so now I'm going to skip up ahead to a equals v squared over r, and we remember, I think, from having done it 5 million times, that means a equals 4 pi squared r over t squared. If you don't remember that, then go back and look at uniform circular motion, because we've done this 5 million times, and it should be so familiar to you now that you couldn't forget it if you tried. Okay, well, t is 1 over f, which means if we want to plug in for t, 1 over t is just going to equal f. So acceleration is really going to equal 4 pi squared r f squared. Okay, so now that's our acceleration. Where's that acceleration come from? Well, that acceleration comes from the gravity, right? So it's a gravitational force. How do we find the force? We're going to say our little chunk of matter on the edge of the star has a mass of little m, and we're going to say the star itself has a mass of big M. Okay, so the force, the centripetal force holding it down, has to be mass times acceleration, which is going to equal 4 pi squared r f squared times, I'll just put the m, I'll put the m at the end. Okay, and that force, this is what the force has to be to keep it in place. It's a lot of variables, well, a lot of letters and stuff, but this is what it is. We know what all these things are. This is given. Actually, it should be a capital R, really, since I was using that over there, but whatever. It's the radius of the neutron star. And that has to equal the force from gravity. So that has to equal capital G, or the magnitude of the force from gravity, times big M times little m over r squared, where r is the radius of the star, right? So now, this is fairly straightforward at this point. We're going to cancel the m's, little m's, and so we want to find the minimum mass of the neutron star. So it's this m here that we want to find. So I'm going to do everything else, shove everything else over the left. And I'm going to say m equals, let's see, 4 pi squared. Let's see, this is going to be r cubed. Actually, I'll put, oh, well, no. Let's see. So it's going to be r cubed f squared over g. So let us see how well this works out. 4 pi squared. So f is 100 revs per second, and the radius is going to be 7 kilometers, which is 7,000 meters. So let's see. Wow, that's not what I want. Let's see. There we go. Yeah, where can I put this? Right, there is no good place to put it. So let's, whatever. 4 pi squared r cubed f squared over g. Okay. 4 times pi squared times r cubed times F squared over 6.67 E minus 11. Now let's see, this gives us a massive, massive answer. So, my God, let's see, 1, 2, 3. Can I do this in, oh crap. Advanced options. There's not even a, yeah, unfortunately. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So this should be 2 times 10 to the 27. So I'm just going to take this and divide it by 1e27 and see what we get. 2.03 times 10 to the 27. So let's see if this works. 2.03 e27. And the mass of the neutron star, I got it right. So there you go. That's number 4.